Let me turn this on so I can be recorded, or I'll forget later. Anybody here own cryptocurrencies? No? So mostly the back, you guys. Does anybody here work in like the blockchain environment, dApps, development? So again, the back row for the most part. So most everybody owns cryptocurrency, but you don't actively work in the field. That's perfectly fine. No worries there. I just wanted to kind of gauge the audience and see who had what, knew what. Does anybody have kind of a fundamental or a basic idea as to what a quantum computer is or what it does? Like a little bit. That's fine. No knowledge is needed for this, so I'm going to try not to, like I said, blow you away or anything of that nature. Nothing crazy, nothing like, we're not going into the deep science or anything like that, mostly because I honestly believe that even the PhDs don't understand the deep science that's going on behind these things, because you can't observe it, so it's hard. Like, science is based on observation. How do you observe the unobservable? Which is kind of what they're trying to do, which is cool. So, good. I'll call that, and we'll get started then. So, I'm Patrick Galloway. I have a degree in computer engineering from the University of Central Florida back in the United States. I am kind of a quantum computing nerd just because a couple months ago I took a blockchain course here at SoftUni, and during the course we had a slide talking about this exact topic, the effects of quantum computing on cryptocurrencies. And like I said, it was really brief. It was one slide. It was just kind of like, here's the brief introduction. These are the things that it does, but nothing more. And so I've always kind of been a nerd. And even when I was in high school, I was fascinated by things I didn't quite understand, things that seemed really difficult. Because, again, being in high school, I felt like that's what the cool kids would do, right? Do something hard, difficult, whether it's sports or being intellectually stimulated or something. So again, I didn't hang with the actual cool kids, but I felt like I was cool because slightly different. So in high school, I found this book called Superstring Theory, which is actually one of the early books on quantum physics. I found it because my high school library was throwing it away. They were getting rid of old books that had crazy nonsense theories and stuff like that. But this was kind of my introduction into the world of quantum physics and later on quantum computing. So at first, I tried reading it. I was in high school, again, a nerd, so I was really good at math. I really enjoyed it. I was like, oh, I've taken calculus. I can read this book. It'll be fine. Get to like page 2 or 3, and I don't know about you guys, but this looks like a wall of text with some formulas and really not much else besides that, right? A little confusing, a little weird. So I was like, you know what? No worries, I'll get back to it. I'll study in college, did computer engineering. I was like, great. I know a lot more math now. I'm great. I know way more calculus than I did in high school. Let me read it. Got about to hear again and was like, I really just don't understand what's going on. So I was like, this quantum thing, it's a myth. People are just kind of talking about it because, again, the book was from the 1950s, so the research hadn't been established or anything like that. I thought nothing more of it until the class a couple months ago. So the first thing I wanted to talk about is quantum computing and whatever the hell that is. Because, again, up till a couple months ago, I honestly thought quantum computers were a myth that people were talking about that was like science fiction in the future. And then I found out, wow, this is actually a real thing. They actually have quantum computers here and now. I want to learn about that. I want to know how the heck they work. So first, just a quick basic overview about normal computers. Because to know how a quantum computer works, we need a basic understanding about how normal computers work right here and now. So a normal computer runs on bits, ones and zeros that work together to make the whole process of the computer run through the CPU. They add numbers, divide numbers, subtract numbers. All those numbers are represented as bits, ones and zeros, running through the computer. In quantum computers, they have what are called quantum bits, in the quantum computing space, they call them qubits. So if you hear about like D-Wave or anything like that, they'll talk about how many qubits are in the computer, whereas our computers now, we say this is like a 64-bit or a 32-bit computer. Same kind of deal with quantum bits. The difference between a quantum bit and a regular bit is that our quantum bits don't just have the 0 and 1 state that we know, they also have a state that's kind of in between that we call superposition. And that's what makes quantum bits really, really powerful and really, really interesting. Now, the difficulty with quantum bits is that while we know they have the state in between, according to the properties of quantum physics, we can't actually observe this state. Because once we observe it, in quantum physics, when you observe something, you fundamentally change it. So if we want to see this state and we look at it, it'll actually look like a normal bit in our regular everyday computer. If I observe the bit, it'll be a 0. I observe it again later, now it's a 1. We never see it in that quite in-between state. And that's kind of the fundamental thing that quantum computing is trying to solve. Now, that was a really rough overview, and I know it kind of went a little bit more into detail than maybe everybody understood, but that's fine. First, we're going to go into superposition. I, again, put a nice, easy formula for everybody to remember, to remind you how nice and simple this is. I don't know what this is either. I know it's a summation of some kind. I have no idea what this means. Let's not worry about that. So there's a lot of quantum physics. There was a lot of talking about this weird in-between state. Instead, let's talk about football. Oh, sorry, wrong audience. Football. So football, right? We play these matches. So like in a couple of months here, we're going to have Manchester United and Real Madrid play. And in this match, we know one of these two teams is going to win, right? So how many people, just out of curiosity, would think that Real Madrid would win this match? So we got at least one. And how many are going to think Manchester United's going to win? A couple more. Okay. So how do we use this in our real life? So what we do in real life is we do betting, right? We have people that are like, hey, I really like Manchester United. I think they're going to win. I'm going to put some money down. And then there's people on the other side that are like, hey, I think Real Madrid's going to win. I'm going to put money down. And they do that before the event happens. And this in-between state is what our superposition state is going to look like. And the odds that are created from these bets are effectively what we look at with the superposition. There's a certain percentage chance that when we look at them, they're either going to be a 0 or they're going to be a 1. So again, that kind of in-between state when we don't know what the outcome is, but we know what the odds are, that's the superposition state. So again, it's not really about winning and losing, it's just about that kind of fundamental thing where this is going to happen in the future, we don't quite know yet. So that's effectively what superposition is. Quantum computers, also make use of another fundamental property of quantum physics, which is entanglement. So again, nice cone, crazy formula. So entanglement, to kind of simplify it in the abstract terms, is the process of linking two photons together or two quantum bits together so that they're dependent on each other. And so again, if that's a little bit complicated, we can go back to football. So with football, we know, again, these teams are going to play, and they're going to be playing at 3 a.m. here. So I don't know about you, but I'm not going to stay up to watch that match. I'm going to be in bed. So the next morning, when I wake up and I read the paper, I'm going to see that Real Madrid won. So if Real Madrid won, then what do we already know automatically without needing any extra information? We know the result, but we also know that Manchester United here, they lost, right? So that dependence, right? When Real Madrid loses, we know Manchester United wins. If it says that it was a draw, we know neither of them won, right? So this interdependence, this linking with each other, is exactly what entanglement does. It says if we have one state of one of our bits and we see it, we automatically know what the other bit is because they're linked to each other. We made them dependent on one another. And that dependence doesn't have to be a win-lose situation. It can also be a tie, right? If this one's a 1, the other one's a 1. If this one's a 1, that one's a 0. So it doesn't have to necessarily be one or the other. It can be both. So quantum computers, again, just to make life easy and to go over the point yet again, because it's very important for understanding how they're going to affect the crypto space, have superposition and entanglement. And we can utilize these two properties to yield more information from any particular computation, than we can in a normal computer, because of that kind of awkward, weird space in between the beginning of the computation time and the end of the computation time. And the difficulty and the challenge with quantum computers is, how do we quantify the space that we can't actually look at and achieve? And so they're actually doing that right now. They have quantum computers. They actually can measure superposition states. I didn't get enough time to research about entanglement states, but we already know that they can do that, because if they entangle two bits and then look at them, they already know which one the other one is. So that one's pretty well established. Superposition is actually kind of the harder thing engineering speak to do, because superposition, you can't observe it. How do we observe the unobservable? So this kind of brings us into our main topic, which is, where are they, right? This is about how quantum computers affect cryptography and cryptocurrencies. Where are these quantum computers? Well, right now, again, we have like D-Wave, we have Google, and also, what was the other big player? I believe Microsoft is trying to make one. Pretty much everybody's trying to make a quantum computer nowadays. Many universities, many big businesses such as Google. I think Facebook's trying to make one. Those kind of people. And they kind of look like old 1950s big computers, right? They're these big, bulky machines. They're very, very expensive. And you can kind of equate the technology to the same thing as 1950 technology. Why? Well, like I said before, it's easy enough to theorize, but they're complicated machines to build and practice, right? We've got to observe this thing when it's in a state that we can't actually observe. How do we do that? How do we measure the difference between the 0 and the 1 state, and how can we tell that it's actually in that superposition? And they've actually figured out a couple ways of doing that, but I don't want to go into that in this talk. That would be a whole separate talk just about quantum computers. So, main question for us is, when are we going to see these in homes? Because if they're that powerful, right, how can I utilize it to either enrich myself, or how do I use it to defend myself from other people trying to enrich themselves off of me? Well, again, because of the technology and where it's at, it's probably not anytime soon. We've got probably like a 20, 30 year range, and then we'll come back here and I'll be talking about how this is like my quantum computer laptop that's showing this to you, and it'll be really awesome. Now, the reason why they're not going to be coming to our homes anytime soon is because they don't solve the same problems that a regular computer solves. So if you think about like hanging a picture in your living room or in your house somewhere, right? Our problem is we have these nails. We need to get them into the wall, but not so hard that we put them through the wall, and not so shallow that they fall out, right? So we got to get them in so we can hang the picture. So you grab a hammer, right? And that's kind of like our everyday computing problems at home, right? We need to use the internet. We need to make an Excel spreadsheet. We need to play a video game, something like that. That's our problem, and computers solve them excellently. Now, if you try to use a quantum computer to solve those problems, it'd be like grabbing a sledgehammer and taking a 10-kilo sledgehammer and trying to delicately tap it against the wall and not break the wall, right, and get the nail in just right. So it's a little bit overkill right now. And again, the technology is just not in a place that's mature enough to take this, miniaturize it, and make it something functional for everyday people. Now, why are we worried about this in the cryptocurrency space? Well, if you believe like clickbait headlines here, you would think that quantum computing is bringing down all cryptography, nothing is safe, everything is going to fall apart, right? It's an imminent threat to Bitcoin security. Worst, you have headlines that are trying to say that, oh, we need to make sure that you buy our cryptocurrency, we're the solution, even though he's a supporter of that cryptocurrency, and by buying it, you're only enriching this guy, right? So we don't want to do that either, because we don't want to act out of fear or or lack of knowledge. We want to make sure that we're an informed decider of our future. So where's the real problem at? The real problem is the speed up of quantum computers versus regular computers. So Shor's algorithm has been created, and what it does is it takes what a normal computer would do in what we would call exponential time. And for the non-programmers, I have a graph in a second, no worries, you'll see. And it takes it down to polynomial time. And again, here's my graph. This is the time that it would take to break a hash. So if somebody was trying to hack you, and you would say, this is how long it's going to take, this is the difficulty, and then this is the amount of strength of that hash. So the more bits that a hash has, the stronger it is. And as you can see right now, our regular computers here in green, it gets really, really strong, really fast. It doesn't take much power on an encryption for a computer to be pretty much not able to crack it. And a quantum computer runs about this kind of speed. And as you can see, if you're in the same place right here, whereas it'd be physically impossible for a regular computer to solve, a quantum computer can do it just fine. But as you can see, they both grow relatively quickly. So the key thing for cryptography in our cryptocurrency environment is that we make it harder. Because the harder we make it, we can get to this point where it's rising exponentially rather than more gradually, right? So the harder and the longer and the stronger we make our keys, the better that they are. So again, the computational speed up just kind of breaks the cryptography, and not in the sense that it's like groundbreaking or it kills it, it's just that it outpaces how strong our current cryptography is in our regular computers, because again, they didn't have to be as strong as they do for quantum. So one of the things that the clickbait headlines will tell you is that it's going to revolutionize mining because of the different natures of superpositions. You can actually calculate the probabilities of whatever the next block is, like in Bitcoin, for instance, because they have a 10-minute block. They think that if you make a strong enough quantum computer, you can actually calculate it before the 10-minute time. And the answer is no, mostly because they have ASICs. Everybody know what an ASIC is? Yeah? So for those of you who don't know, it's a specialized piece of hardware that only runs the mining algorithm, and it runs like 10 to 15 times faster than the theorized 15 years in the future quantum computers will run. So they're running way, way faster than anything a quantum computer is going to do, even in like the foreseeable future, even 10 years down the line, which is kind of, you know, where you want to have your investment portfolio range go to. So quantum computers are going to be able to crack your private keys, though. This is where the scary thing lies. Not in the fact that they're going to mine all the blocks and then they're going to get power over everything, but that they can crack individuals' wallets and get their money. So it doesn't matter if you mined the block or didn't mine the block, or you bought Bitcoin or didn't buy Bitcoin. If they can take your private key and steal your wallet, they have your money. So that's bad, right? That's a bad thing. We don't want that. And so the reason that this is a problem is because currently we use elliptic curve cryptography to encrypt our wallets on most cryptocurrency platforms like Bitcoin and Ethereum, and pretty much all the major players kind of follow that model. So they all use elliptic curve cryptography to encrypt your wallets. And those are very short key lengths for a very powerful encryption. So the encryption is way too hard for a normal computer to break, but quantum computers, again, because that key is very short, it's not as difficult. So the easiest way for elliptic curve cryptography to adjust is to lengthen the key, but there's another problem with elliptic curve cryptography, is that it's a graph. So the graph kind of looks like this. Let me see if I can draw. Okay, so a normal elliptic curve kind of looks like this shape, kind of. And what your private key does is it starts on a point. Oh, here, let me draw a coordinate grid for you so that it's a little easier. So what your private key does is it kind of finds a point on this line randomly, and then you encrypt it with a password, and that will move it somewhere onto this graph. And so what you have now is a dependence between one point and another. An entanglement, right? That linking between two things can actually crack the elliptic curve cryptography without even needing to be as powerful as just saying, like, we're going to hash away and we're going to brute force and break the key. So there's actually multiple ways that quantum computers can break elliptic curve cryptography that are beyond the key length. So that's why they're kind of, in my opinion, not that great. And that's probably one of the things we definitely need to move away from. So again, how can we react? We need to move away from elliptic curve cryptography. Elliptic curve cryptography is going to get me today. I'm sorry. Tongue twister. So we need to move away from our elliptic curve cryptography. Man, I thought the last time would do it, but it didn't. So because it's just inherently not safe from quantum attacks. So if a quantum computer wants to take your key, if you're using elliptic curves, it doesn't matter if we make the key length 10 times bigger than it is now. If they make entanglement strong enough, which again, this is all kind of a little bit theory, but they're much closer to having an entanglement system that's that powerful than they are from brute force killing your key, then these will still be unsafe. Instead, we can move to a hash-based system. All cryptocurrencies nowadays use SHA-256, or not SHA-256. Yeah, SHA-256 or SHA-3, like the Ethereum. I was thinking of Kershak. I'm sorry. Head got jumbled on that one. So, which is just a variation on SHA-3. All we'd have to do for a hash-based system is, again, increase the key length. And because a hash-based system doesn't have that dependent kind of relationship in it inherently, like the elliptic curve does, then this isn't subject to an entanglement attack. So that's all fine and great, and we can totally move away from these things. But the biggest thing about cryptocurrencies is consensus, right? We have these nodes, these computers that are running, and when somebody wants to update the software, we need to make sure that everybody agrees, right? Well, what if in the future, 5 years down the line, when quantum computers are more of a threat, people are like, no, it's still just fairy tale, right? They thought it was science fiction still because they didn't read about it or didn't hear about it. People say things like quantum safe and stuff like that all the time, but they're just using it as buzzwords, right? They don't really know if it's quantum safe or what that even means. Up to 2 weeks ago, I could have told you, yeah, Bitcoin's quantum safe because of the decentralized whatnot, but I would have no idea because I didn't do my research on it. So importantly is, how are you going to react to this situation? Because you guys actually have the power to have a deciding vote in whether these cryptocurrencies do move forward to becoming actually quantum safe, to moving towards a hash-based key system, towards growing. And how do you do that? You just download a node yourself. They're free to download. The hardware to run a node versus a miner is actually pretty much, it's very cheap. You could get a regular home computer with a good internet connection to run a node, because all they're doing is sending information, yes or no, back and forth, and checking to see if a new mined block is valid or not, and if you want new software or not. So my biggest takeaway for you guys is to go ahead, download a node. It can be Ethereum, it can be Bitcoin, it can be whatever coin you want on CoinMarketCap. They actually have all of the white papers and all of the places that you can go to download the software. And then that way, that gives you that deciding voice. Now you're physically invested in whether that new technology that they already have, because making the key links bigger is trivial. We've done it several times in the past. There's several encryptions that we've blown past, like MD5 and other things of that nature. So for me, that's it. Did you guys have any questions? I'm happy to answer them. I know it's kind of a broad topic to do in such a short period of time.
Yeah, I have a question. So
Yep.
how does the concept of qubits and entanglement allow the computers to speed up cracking the algorithm?
Okay, so with entanglement particularly, what you do when you sign a normal transaction in Ethereum, for instance, right? You have your signature, which is an encryption of your private key and your public key, and you have the formula as this. You have the thing that you're about to encrypt, which is your private key, plus some stuff equals, your public key. And you put that in the transaction hash. You put your public key and your encrypted private key. All you need to do is entangle the public key with the signature, reverse that equation, just subtract the two or do whatever, what a decryption would be in reverse, or attempt to, because for normal computers that's physically impossible, but quantum computers can at least try. And then what you would do is you get an entangled set of bits, or you could run it through forward again. You have the finished product, you have the encrypted thing, you can run it forward, get the public key, and now you have the entangled private key. And again, that's still technically theoretical. They've done it for very small key sizes. So I'm talking like 4 to 5 bits, whereas in elliptic curve cryptography right now, we have a 160-bit key. So it's progressing, and it's doubling pretty much. That quantum bit size is doubling every year to year and a half. So actually they almost doubled it from a couple months ago to today, or not today, but recently they introduced a new, I think Google announced a 20 qubit quantum computer, and the biggest one before that was like 6, which was D-Wave, which I had on the slides. So that's how you do it with entanglement. With superposition, what they do is, I don't know physically how they do it because I've never found an article that accurately describes it, but they somehow can read the percentage of where the quantum bit is leaning and kind of those in-between states. And so they read that as the program's running, and what that does is it gives you again, kind of like I said before with the betting charts. You have a betting chart and you can have a good idea as who's going to win and who's going to lose beforehand. They actually use that to calculate lots of things. They use betting, to figure out who's going to be like the next president of the United States. For instance, they do that all the time. They actually find that people just betting on it win almost every single time. I think Great Britain used the betting system, and they've gotten the last like 12 presidents correct with their betting system. So very accurately, they can narrow down that list of possible private keys to actually hack. So now instead of brute forcing every private key in existence, all 256 bits, in fact, like with the exclamation point behind it because the word left my brain, which is a huge number of things to go through. Again, a normal computer can't do that. A quantum computer probably actually can't do that. But what it can do is it can make that list, it can reduce it, and now it can run through all of those, which is a much more achievable task. And again, to do that, we're talking, that's probably like 10 years down the line from now for the 160-bit elliptic curve cryptography, probably about 10 years out. Maybe faster if they continue at the pace they're going with getting quantum bits. But they're still having some troubles with the bigger computers. They can actually get more than 20 quantum bits, but they can't hold the superposition state because it's very expensive. It takes a lot of time and power, and right now they use a couple of methods like lasers, and they actually use like liquid nitrogen to try to get the atoms down to almost 0 degrees Kelvin. So almost absolute zero, so they can actually observe it long enough to release it and to let it finish its calculation. So again, it's something that's going to happen, and that's kind of down the line. Any other questions, comments, concerns?
Okay, so if elliptic curve cryptography can be broken by quantum computers, why is hash-based keys not broken?
Because hash-based keys don't use the same kind of linear architecture. So in an elliptic curve, you have your private key, which is actually a number. It's just a randomly generated number, either off of, again, a random number generator or a mnemonic. If you've ever used MetaMask and had to type in all the funny words, it's just a random number generator, and they use those words kind of as placeholders for numbers. And then when you type in your password, they use that to encrypt the private key and take it to a point on the curve. So they plug that in in the equation of whatever that elliptic curve is, and then you get a random point. So usually it's a really big prime number, and you take whatever your password is and you multiply that by another really big kind of prime number, and that kind of scrambles everything and makes it very hard for a computer to figure out. And they really can't go backwards from that equation effectively. It would take way too long. You had a question?
Yeah, so usually with like these kind of new technologies, in the beginning they're a bit wonky, right?
Mm-hmm.
Work as expected.
Yep.
You know, so is that the case with quantum computers, where like when they do come out, people are like, okay, it's ready to go, let's start cracking Bitcoin? Or will it be like, maybe we'll start slow and then build it up to a respectable degree?
So right now I feel like they're in that stage. They're like, oh, you get the clickbait headlines where they're like, they're doing it today, bro. They're going to kill it. They're going to take everything down in the next 5 years. And that's really not the case. Like I feel like you have 10 years before you have big players like IBM, Google, Microsoft, colleges that will actually have the power to do that. And of course governments will have that power too. So, it will be doable, and there are people actually working on the cryptographic nature of it, just because that's a very valuable asset that quantum computers have over regular computers, which is most of the reason why they're investing in the technology, all of these agencies, because they want to be able to like get or figure out how to break hashes and stuff. That's kind of like a mathematician's dream, right? Is to break a cryptographic hash. So, it's not mature right now, but maybe in 10 years, not everybody will have it, but enough big players will have it that it could be a problem, right? If Google has a quantum computer that can break elliptic curves, they can just steal everybody's Bitcoin wallet. What's to stop them, right?
It's different from Google doing it versus like a small-time hacker, right?
Yeah, exactly. And so yeah, you're going to have big players making themselves bigger, but when it does come to everybody else, right? You want to be beyond that problem. You don't want Google stealing your money. You don't want anybody stealing your money, right? That's kind of the whole point of getting Bitcoin or Ethereum or getting into crypto at all, is that it's secure and it's away from these outside forces, right? It's decentralized and it kind of has that inherent safety net built in.
More comment?
Yep.
I read that the public key of Bitcoin is actually pre-hashed as well. So like,
yeah, it's not a straight elliptic curve. It's a little bit more on top of that, but it's still not, because the end result is only the 166 bits or whatever. I don't remember the exact length of the Bitcoin key. Excuse me. It's still hackable by the quantum computers and about the same effectiveness, because at the end of the day, again, with entanglement, they just need to like link one of the bits to one of the other bits, and they can send it through everything, and it doesn't really matter what happens in the middle, right? It doesn't matter that Real Madrid was 3 up at 10 minutes ago. If Manchester United scores 4 goals, they win, right? We don't really have to care about the in the middle, because the end result will link them. It has nothing to do with actually seeing the game, right? Any other questions? Because again, these are really good. I strongly encourage anybody to download a node. Like I said, it's very inexpensive. You can run it pretty much on a home computer with good internet. I've looked into like the Ethereum node, for instance, and if you don't include the miner, you can get away with like an i5 and a little bit of hard drive space, maybe like a terabyte spinning drive, internet connection, and you're good. So that's it for me. If you want to get in contact with me, this is my email, and anybody has more questions later you didn't want to ask in front of the class, then you can come on up, and I'm be here for a little bit. Thank you so much.